For this video, let's try to identify the reflection of point 25 about or on the line identified as negative 4x plus y equal to 4. So if it's actually illustrated on this Cartesian plane, we are to identify our, let's say our point x is our point x, okay? Our x is a 2 and 5. So we're going to identify the reflection of point x. It's actually either x prime or what we usually know using our formula, the reflection of x along line L. So our 0.25, considering that our Cartesian plane here is of grid 1, we have 1, 2, and 1, 2, 3, 4, 5. This is where we could find our x. The next thing here is for us to identify the graph of the line so that we would know where is the possible location of our reflection. Okay, because if we're going to consider the y-axis, if this is our point of our line, so the point of reflection is actually somewhere on the second quadrant. If it's the x-axis, so its reflection is somewhere here on the fourth quadrant. So for that, let us try to graph our line L. It's not necessarily needed here, especially that if we already have the formula for the reflection of x on long line L. It's actually x minus twice x minus p and the unit normal vector times the unit normal vector. We have this formula, but just for the illustrations that we could actually be guided on our possible result, because there might be some instances where our results are actually just by the signs will be incorrect. So we'll be guided. Let's have this. So again, our point x is at 2 and 5. So our line is negative 4x plus y is equal to 4. To graph that on our Cartesian plane, let us use here the intercepts. So for our x-intercept, again, this is not necessarily needed if you are just solving for the reflection. But for illustration, let's have this. Let y is equal to 0. So you will have here minus 4x. Again, this is our L, right? Is actually minus 4x plus y is equal to 4. So you have minus 4x plus 0 is equal to 4. So minus 4x is 4. X is negative 1. So our x-intercept is at negative 1 and 0. So it's actually negative 1 and 0. This is negative 1 and 0. For our y-intercept, let x be equal to 0. So you have minus 4 times 0 plus y is equal to 4. Y is equal to 4. So it's 0 and 4. So 0 and 4 is here. This is our y-intercept. 0, 4. Connecting them using a line. Hopefully I could draw my line well, assuming that my line is accurate. So you'll have here this being our line L, described as minus 4x plus y is equal to 4. So by this, our reflection is along this line or about this line is actually located somewhere here on the second quadrant. And the signs of the second quadrant are actually negative on x and positive on y. The reason for that is for us to be guided, of course, in our results later. Okay, anyway, that would be verified later as well. Okay, my graph or my drawing may not be also accurate, so I'm not going to illustrate the location first. We'll have it later as well. So let's talk about the reflection now. As we have x already identified here, that would be included in this formula. P, it's up to you which you will be using. You can use the x-intercept or the y-intercept. It's up to you. And then our n sub u or the unit normal vector, it's actually the normal vector of magnitude or length 1. So we are going to introduce or reintroduce normal vector. The normal vector will just contain a and b if the direction vector of the line is not identified. And your a is actually located here. This was our a, so negative 4. Our b is the coefficient of y, which is 1. So our normal vector is actually negative 4 and then 1. The coefficients of your x and y in our line. But this is not what will be implemented here because it's a unit normal vector. So solve for the unit normal vector is actually equal to the normal vector over the length of that vector. So the length of the vector n or normal vector is actually the square root of the sum of the squares of the components, negative 4 squared, 1 squared. You will have the square root of 4 squared is 16. you'll have here plus 1. So the length of your normal vector is actually 17. So our unit normal vector will have, by the way, instead of this, we may also use negative 4 and 1 using parentheses. We were using this before to differentiate that from any point, because this might look like a point, but just for this, we'll be using the parentheses, and hopefully this is clear, over square root of 17. Or the unit normal vector could also be written as negative 4 over square root of 17 and then 1 over square root of 17. This is our unit normal vector. By the way, let's not rationalize it. A certain process later on will of course rationalize that in its own sense. So let's return to the formula on the reflection, which is actually the meat of this video, just for the previous illustration, just for us to be guided on the possible location. The formula is that x minus twice x minus p, and then unit normal vector times unit normal vector here. Our x is identified here, 2, 5. Okay, 2, 5. Hopefully the space are enough here at the bottom. Minus 2 times 2 and 5 for our x, and our p, again, it's up to you. Let me use this one here because it has a smaller value and it's easier for me to implement that later on. So our x-intercept, you could even use the y-intercept, but I'll be using this, okay? And then your unit normal vector, which is negative 4 over square root of 17, 1 over square root of 17, the inner product of that, times negative 4 over square root of 17, and 1 over square root of 17, the unit normal vector still. So let's do this step by step. Okay, so we have here 2 and 5 minus, again, this is 5, sorry for that, 5. Then minus twice, let's combine this first. That's 2 plus 2, 1, because 2 minus negative 1 is a 3, and you have 5 minus 0 is 5. Its inner product together with the unit normal vector. Okay. Okay. Then the result of that together with the scalar of 2 here will be multiplied still with the unit normal vector identified here. Okay. So still this is 2 and 5. So you'll have your minus 2. Now, if we talk about inner product, you're simply going to multiply the corresponding components. Okay? So with that, and take note, you're going to add them, hence the result is actually a scalar quantity. 3 times negative 4 is negative 12 over square root of 17. And then 5 times 1 is plus 5 over square root of 17. It's now scalar because you can add them. Times the other unit normal vector outside right after you have simplified your inner product. So this is actually 2 and 5 minus 2 times, this is negative 7, right? Negative 12 plus 5, negative 7 over square root of 17. Times again, you have negative 4 square root of 17 and 1 over square root of 17. Multiply that, 2 and 5. Now you have plus 14 over square root of 17. Now a scalar times your unit normal vector. This is 4. If I'm correct, is it 4? Yeah, 4. Minus 4 square root of 17 and 1 over square root of 17. Now, this is scalar, so we can now multiply this to that. So you will have here 2 and 5 plus, so you can use your calculators there. 14 times 4 is of course 56. Now negative 56, right? But look at the denominator. When you multiply square root of 17 to square root of 17, it's just 17 in itself. And then 14 times 1 is 14, again over 17 here. So you could have here this form, 2 minus 56 over 17 and 5 plus 14 over 17. And take note that our presumed location is at the second quadrant, so it would be having negative value for your x but positive value for your y. Let's see. So we have 2 minus 56 divided by 17. Please use your calculators. And again, in the form of fractions, you will have your negative 22 over 17. And then you have 5 plus you will have 14 divided by 17 or 15 over 17. Again, by fraction, you will have here 99 over 17. As you can see, our x is negative, our y is positive. Clearly, this can be found on the second quadrant. Let me copy this just for the purpose of illustration, because let's try to plot that here assuming that we already accepting that this is really the correct answer. Okay, so I don't know if this can be, let me rewrite that, over 17, 99 over 17. So 22 divided by 17, that's negative 22, by the way, is 1.29. Round it off into two decimal places. So by the way, 1 point here, negative 1, negative 2, so somewhere here, negative, right? Negative. And then for our 99 divided by 17 is 5.8 approximately. So you have 1, 2, 3, 4, 5, somewhere here, also almost 6. So by connecting that, this is the location of your x prime, or your reflection of x along line L. And as you can see, this should have the same distance with this one here and that. So that's the reflection, and this, again, it's on the second quadrant. We can see it's really clear that our answer is correct, because if it so happened that in our process earlier we find out this is positive, so it's already an indication that our answer is incorrect. Or even in the process here in the middle that yielded to this result is incorrect, because our point of reflection should be on the second quadrant and it should be negative, right? It should not be positive. Or the other way around, if this is negative, so again, it's incorrect. So that's our guide of illustrating that earlier. So we have solved already the reflection of 0.25 on the given line. Thank you very much for watching.